So welcome to the last afternoon of the school. And for me, it's a pleasure to present Gabriela Estevez, and she will talk about hyperbolicity of renormalization for bicubic circle maps with bounded combinatorics.
So thank you, Cristina. Are you hear me? Okay, thank you for the invitation. And thanks to the organizer for the opportunity to talk in this wonderful conference in honor to Lorenzo. Okay, so today I'm going to talk about a joint work with Michael Yampolsky from University of Toronto. Okay. So I will start with a motivation that probably most of you know the history in the case of unimodal maps. So in the 70s, when the mathematicians were studying the quadratic family, x to the power of 2 minus c, they found the existence of some parameters, Cn, where the periodic double bifurcation occurred. So this is the picture here that you must see once at least. So these parameters converge to a fixed parameter, C star, which is this value. And the observation here is that the convergence is exponentially, and exponentially with this number that I will call just lambda, but in the future I will give it a name. Okay, so there exists of parameters, and the parameters converge to the fixed parameter, and we know the velocity, the rate of the convergence. So, and moreover, if you consider another unimodal map, family of unimodal maps with quadratic critical point, it was observed the existence of another parameters converging to another fixed parameter, but they observe that the same rate remains. So this constant appears in each family of unimodal maps, and since the constant is independent of the map, we say that the constant is universal. So this constant is called Feigenbaum constant. Feigenbaum was a physician, because it was observed in physics first. Okay, so the question is, how can we explain the existence of that universal constant, the Feigenbaum constant? And it was conjectured in the 80s by Feigenbaum and two mathematicians, Colette and Treser. They were independent. They conjectured that the duplication that we see of the period represent an action of an operator, and they call renormalization operator. This renormalization operator is acting in the space of unimodal maps, so it's acting in an infinitive dimensional space. Okay. So they say that the renormalization has a unique fixed point that they call F star, and they observe that the spectrum of the derivative in that fixed point has a unique eigenvalue, whose value is equal to that constant Feigenbaum constant lambda. So this eigenvalue is outside the unit circle, and the other is inside the unit circle. So this conjecture was in fact proved. Now it's a theorem. There is too many people that work in this theory. More or less the last part was proved in the 99, but it's a long history. I wrote some names: Lanford, Sullivan, McMillan, Lewis, but there are more people that work in this. So what they prove is that in effect there exists a space of infinite dimension, which is the complexification of these unimodal maps, where the renormalization acts, and moreover, renormalization has a unique fixed point, F star. The renormalization in that fixed point is hyperbolic. So there exist two transverse manifold, the unstable and the stable. So any map, sorry? No? Okay. So any map in the stable manifold on the renormalization goes to the fixed point and for future iterates, and any map in the unstable manifold for past but future iterates repel from the fixed point, and the rate is lambda. So lambda is the Feynman constant. So the dimension of the unstable manifold is 1, and since we are in the infinite dimensional space, the codimension of the stable manifold is 1, codimension, okay? So this is something that we understand in the case of unimodal maps. So this is the picture, more or less. I take this picture from a survey written by Ljubich, and I think this is a very nice survey. If you are interested in know more about this history, it's a good start. So this is the fixed point. You have the unstable dimension, unstable manifold with dimension 1, and this is the stable dimension. So if you consider a map of family of unimodal maps, this will be a curve in this like this, and the intersection with the stable manifold will be the corresponding map with the corresponding parameter C star that we saw in the beginning. Okay, so that happened with any kind of family of quadratic maps. Okay, so this is done in this is something that we understand in the case of unimodal maps. So now,
Gabriela, can I ask a quick question?
Yes.
So who is this map F star?
It's a fixed point of the renormalization. So they prove that there exists. So on the renormalization, this map is fixed, but on the renormalization, these maps, which are the corresponding parameter that we know that there exists, they go to the fixed point on the renormalization. But this is fixed point.
But do people know the formula for this F star, or?
I think in some cases, yes. I think in the quadratic case, they know who is the map. Yes. Okay, so, okay, thank you. So now we go to the case of unicritical circle maps. So now we change our space. We were in the interval maps, now we go to the circle maps. And we are asking what happened in that space. So we are interested in real analytic unicritical circle map, which is just an orientation preserving circle homomorphism with irrational rotation number and only one critical point, which is not degenerate. Okay, and the criticality of that critical point is usually 3. It's an odd number. It was done for all odd numbers, but usually it's the criticality is 3. So morality in a neighborhood of the critical point, if you consider the leaf of the circle map, which is an interval map, you will see the map x to the power of 3 around the critical point. So this is the critical points that we are interested. Okay? So it's an inflexive critical point. Okay, so these maps were studied in the 80s, well, since the 80s. And the first important result of these maps is due to Jokos, who proved that these maps are topologically conjugated with the corresponding ridge rotation. So your map has an irrational rotation number, and by Jokos, the map is conjugated with the irrational rotation. So the rotation with the same rotation number. Okay. So in particular, we know that these maps, those maps do not have periodic points because the irrational rotation doesn't have periodic points. And moreover, if you consider 2 of these real analytic unicritical circle maps with the same irrational rotation number, they will be topologically conjugated between them. Okay, so for unicritical circle maps, it was proved the hyperbolicity of renormalization, and this was done by Yampolsky. So it was in the I think the year is 2002. So in the case of the circle maps, it was not easy there in that moment to find a suitable functional space where you get the hyperbolicity of renormalization. So morally, you can see the first return map, because when you define renormalization, you are considering the first return map. So you can see that return map as a circle map. And this circle map can be extended to a neighborhood of the origin in the complex plane. So you are more or less in the R2 plane, and there you get a extended map that represents the first return map. So you can extend in a neighborhood, but you maintain the real line. So you have a cylinder map. I will give a picture, maybe it will help. So in this case, the renormalization is called cylinder renormalization, and is defined between cylinder maps. So the renormalization in this case takes maps in the cylinder maps, and returns a cylinder map. So morally, you have something like that. Let me write this. So you have your return map, which is a circle map, and this return map can be extended to a domain here in the complex plane. Okay, so this extension, so this corresponds to the circle, right? Because we are your map is a circle map, and this extension, which is something that we call butterflies, will extend to a annulus here around here in the cylinder. So the part in the real line corresponds to the circle map. Okay, so this is what we have. These maps goes to this complex plane, and this is where you get the cylinder map. So now, if you want to come back to the cylinder map, because I say that renormalization takes maps of the cylinder and return maps of the cylinder, you will consider. So the question is how I return to the cylinder. So this is a little technical, but the idea is that you can find a fixed point. So this red point, yes.
Sorry, I don't understand this. Where the butterfly, what the butterfly is.
Yeah, well, yeah, you are considering real analytic maps. So the maps have an extension around, not only in the circle or not only in the real line, if you are looking for the leaves, but you can find a fine extension because your maps are real analytic. So they are defined in a bigger, in a neighborhood of the.
You extend them. You take a lift of the map to the real line, and then you take an analytic extension.
Yes,
in the neighborhood of the real line. In the
yes, there are some steps between, yes. But the idea is that you can extend the definition of your map, of your return map.
Yes.
As a holomorphic map. This is good. This is the thesis of Edson de Faria. He proved that in his thesis. Okay.
Okay.
Okay. So this red point, it will be, oh sorry, it will be a fixed point of the first return map. And this point, if that point will be in the real line, so if it is here, then you will say that the return map has a fixed point. But we say that the original map doesn't have doesn't have a fixed point because we are looking as a irrational rotation. So we don't have fixed points. Okay, so that point exists when the rotation number is irrational. So that point exists and exists in that part of the plane. So it's not in the real line. And the idea is consider the conjugate points, and we form something like a moon. So we have a curve that a path that connects the 2 points, and we consider the action of the phase return map in this region. So the boundary of the moon is the image by the phase return map of the path that connects the 2 points. So if you consider the return in that moon without the extreme points, you will arrive to a cylinder. So this by uniformization theorem. So this is a Riemann surface, and by uniformization theorem, you will come back to a cylinder map. So this part inside the moon in the real line will project to a map in the cylinder, but that preserves the circle, which is the cylinder renormalization. So this is more or less the idea of renormalization, of cylinder renormalization. Okay. So the idea is consider the phase return map and find a way to define this from the cylinder to cylinder. And why they do that? Because this space of maps in the cylinder form a Banach manifold. So this is why they do that in that way. Okay. So this is more or less what is cylinder renormalization. Sorry for my design. So, okay, so in the case of unicritical circle maps, it was proved the hyperbolicity for any odd criticality. So criticality 3, 5, 7, 9. So this is the theorem that I was telling you. Yampolsky proved the existence of the horseshoe attractor for renormalization. So this is an infinite dimensional horseshoe for any rational rotation number. And what we know is that what he proved is that the attractor is hyperbolic, but with a single unstable direction. So, and the stable direction has codimension 1. So the picture is like the same as in the unimodal case. And moreover, he knows that the stable manifold is made of these real analytic circle maps with the same irrational rotation number. Okay, so they have a picture of the hyperbolicity, and it's more or less the case of unimodal maps. Okay, this was done in the unicritical case in 2002. So what we can say about more critical points? So what happens if we consider another or more critical points? This is so this is our interest. We are in this talk interested in bicubic circle maps. So a bicubic circle map is just a circle map that has 2 critical points of degree 3. Okay, this is our definition. So okay, so for these maps, we know just few things, and this is due to Yampolsky again. So 2 years ago, he proves he extended the cylinder renormalization for the case of maps with more than 1 critical point. So this is something that he did, and he proved that there exists periodic orbits for that cylinder renormalization. So he did one step. He proved the existence of the periodic points. He proved that the periodic points are hyperbolic, but in this case, the unstable manifold is dimension 2. So it's not 1 as before or as in the unique modal case. So we get 1 more dimension of the unstable manifold. And these periodic points will correspond, so under renormalization, the periodic points corresponds to bicubic circle maps with quadratic irrational rotation number. So, okay. So, okay, so we have two unstable directions. One of these directions depends on the rotation number, how the rotation number changes, and the other depends on the distance between the two critical points. Okay, because now we have a new invariant. When we add another critical point, we have a new invariant, which is given by the invariant measure. There exists an invariant measure for these unicritical maps, and the other invariant is the measure given by that invariant measure between the two critical points. So this is something that we didn't have when we get in the unicritical case. And just to recall you, these quadratic irrational numbers are all these irrational numbers with periodic fraction expansion. So you have these constants in the continuous fraction expansion, and they repeat. There exists some k where this decomposition where this sequence repeats. Okay, so this is what he proved for bicubic. So what we have is that there exists in a certain way a bigger invariant set of renormalization, which correspond exactly to the closure of the periodic point. So the closure of the Yampolsky set for bicubic circle maps. And this was done together with Daniel. Yeah.
I have a case that maybe is, I don't know if it's completely silly, but when you have these two saddles, you have a kind of homogeneous relation between them, or this is an infinite dimensional space that is much more complicated?
I have until now he proved the existence of periodic points on the renormalization, and he knows that they are hyperbolic, but I don't know if they have any relation between one and the other.
Then you have infinitely many of them.
Yes. Yes,
and they accumulate to the original ones, for instance. And probably you also have a uniform rate of contraction or things like this, or you don't know.
Yes, we will like to have this, but until now we just know that there exist periodic points. Okay.
Okay.
So the idea is to extend the hyperbolicity results not only for the periodic point but for its closure. So the closure is this set AB, this AB set. So this is something that we did with Daniel Esmania and also with Michael Yampolsky last year. So we find a compact space of bicubic circle maps, but this time the rotation number changed because we are in the closure. So I will explain why this is the closure. So this set is invariant. So this is a space of bicubic maps. So this is an infinite dimensional space. But I know that when I renormalize that in a map in that space, I will get a map in that space. Okay. So what is done? What happened with that set? So if I consider a bicubic circle map with bounded type rotation number after renormalizations, after many renormalizations, I will arrive to the AB set. So my set is an attractor of the renormalization. And moreover, and this is what we observe, is that this set, AB, contains unicritical circle maps of order 9. So we began with maps with two critical points of order 3 each, but now we can get maps with order 9, so unicritical. And that happens, and that could happen, and when happens is when one critical point goes to the other, because when we do renormalization, we consider first return maps. So we go around the circle and we come back to a region, to the initial region. So when we go to the circle and we arrive to the original region, we can take one critical point. So one critical point can come back to the other. So not to itself, because we don't have periodic points, but one can go to the other. That could happen. So this set is in that sense bigger than the set that Yampolsky have found. Okay. So just why this is the closure? Well, if you have a bounded type rotation, rotation number, so you have a sequence like this, sequence of continuous fraction expansion. So all of them are bounded by a constant. But the set of quadratic irrational numbers, the set that Yampolsky was interested, is dense in that sense, in that set, because if you have bounded type rotation number, then you can consider a sequence of rotation number, just taking the first element of the fraction expansion and repeatedly then. So pk will be a0, a1, ak, and again a0, a1, ak, and so on. So this sequence of pk will convert, will convert to the original row, right? We are considering these numbers. Sorry, this should be an. So the set of quadratic irrational are dense in the bounded type, and that's what I said. And the unicritical of order 9 are the limits in a certain way of the bicubic under renormalization. So that's what I said before. If one critical point goes to the other for some iterate, then what we get is a unicritical circle map. So the renormalization gives me a unicritical circle map. Okay. And once you take the other critical points, you will be unicritical for the future iterates or the future renormalization. So with this renormalization, you can keep the critical points, or you can lose one critical point, but of course you cannot create new critical points. Okay. Okay, so our goal is to extend the results of Yampolsky on hyperbolicity, but for our set, for the closure AB. But there is a problem, as we can see, when the two critical points collapse, and that could happen, then the two unstable directions collapse into one, because when the map is unicritical by Yampolsky in the 2009 year, he proved that for unicritical, we only have one unstable direction. So this is true. So we will have in our space, we will have points with two an unstable manifold of dimension 2, and other points which unstable manifold is dimension 1. So what we can do, and the solution is maybe we need to find another functional space where the collapse does not happen, and where you can embed the space of circle maps or the cylinder maps. And this is what we do with Michael. This is work in progress. So we define a functional space, which we call the space of pairs, such that we extend the renormalization operator as analytic operator, because it was analytic in the case of the cylinder, of this from cylinder to cylinder map. So we can also extend our attractor, our AB set. So there exists an attractor for renormalization in that space, and corresponds to the projection of our original attractor. And in this space, all points in the attractor has unstable manifold of dimension 2. Sorry, I repeat that part, sorry. So unstable dimension of dimension 2, okay? This is our theorem, and more or less what we do is, when you consider, just in the case of the circle, when you consider the first vector map, you go to a place to another, but you go through the circle, okay? So in a certain moment, you will catch one critical point, and there are other moments when you don't attach the critical point. So something like that. So you have, so you want to consider this return map, which I call F, and in certain moment, you start, depending on when you start to a place to another, and this could be a diffuse if it doesn't contain a critical point, because the circle in this case only have 2 critical points. So that could be the case when you don't have critical points here. But maybe you attach here 1 critical point. So this is a critical point. In that case, your map is like x to the power of 3. This is what I said at the beginning. And you arrive here to the critical value. So maybe there are no more critical points. And then you arrive to another place with a diffuse, assuming that we don't have more critical points. And when we touch another critical point, our map is like x to the power of 3. And probably then to come back to the complete the return map, maybe it's a diffuse because there are no more critical points. Only these 2 are critical points. Okay. So this is critical value. So you have a decomposition like this, and I wrote something like this. So this is in the circle case. So in the butterfly, you will see that these diffuse are in fact conformal maps, and next to the power of 3 is the cubic map usual. So you have a decomposition, and this decomposition is unique. So what we do, of course, we need to use the uniformization theory coordinate, which was defined in the moon when I did my first picture. And with the help of this uniform coordinate, we define this pair of maps. So the return map, the map that is obtained, but the first return map, we associate this tripla, and we can prove that this space of tripla is also a Banach manifold. So in that space, we will not lose, even if the map, if the critical points, if one critical point goes to the other, we never lose one of these components. So we will always have triplas. So that's why, and we can extend on the renormalization, and in this space, we cannot see the collapse of the critical points. So, so this is all. Thank you. Happy birthday, Lorenzo.
Let's thank Gabriela. So any question or comments? You can open your microphone.
So the unstable directions are generated by what exactly? I mean, you have 3 unstable directions, or?
No, sorry, I don't. No. You have 2 unstable directions.
Okay, so you expect that if you have any critical points, you have n minus 1.
So in the case of one critical point, you have one unstable direction. Even so, what is the, I don't know, the conclusion? Maybe is that in the unicritical case, we don't see the problem with the dimensions, because we all only have one critical point. So maybe when we add another, so maybe when we have 3 critical points, we will have 3 directions and so on. So the problem was that we cannot see in the space of cylinder map. So we can go to another space where we can see that. But as people that work in this problem say, it's very important to understand and to identify the functional space where you work. So hyperbolicity depends too much on the space of functions, the infinite space of functions that you are considering. So when you add more critical points, you expect to have more dimensions. Yes.
Mhm. Thank you.
Thank you.
Lorenzo?
I have two questions because in some slides you wrote that there are unstable directions that collapse. I didn't understand this quite well, but my question is, maybe if you increase the number of critical points, you may have periodic points having different unstable number of unstable directions, or
yes.
always.
Yes. Collapse in the sense, yes, because the other direction depends on the distance on between the 2 critical points. The distance is 0, so you will not get that direction. So collapse in that sense.
That means that you will have point having 2 is unstable direction and another points having only 1 is unstable direction.
Yes. So
and
we can.
You may have cycles there.
Probably, I don't know. So the idea is to find a place, a functional space where you always have 2 dimensions, no? Because the collapse of critical points can happen or not. So
No, of course, but okay, thank you.
okay.
Any more questions? If there are no more questions to Gabriela, let's